Okay, so an Eisenstein integer is a non-unit Gaussian integer a plus b omega, where omega times 1 plus omega is equals minus 1, and a and b are integers. So we're going to try to write a code for it. There's the original code here, actually. We're going to try to write it from scratch, and we got two tasks. The first one is the financial here as their complex number values the first 100. Einstein primes near zero by the norm order. In a second, we're going to scratch, we're going to display the plot of the first 100, 2,000 such numbers. So let's understand firstly what is an Eisenstein integer and what's an Eisenstein prime. So we're going to just take this verbal description, we're going to write a code for it, okay? So an Eisenstein integer has kind of a similar form of complex number, but it's not exactly informative of complex number. It's not a complex number. Gaussian integer, on the other hand, is a complex number, but it has integer, real, and imaginary parts. Here, an Eisenstein integer has not an imaginary unit, but has this a plus b omega format. That's where one gives us a constant that includes both real and imaginary parts. And also we have this expression for omega here, and we know that a and b are integers. Okay. So as with the Gaussian integer, any Eisenstein integer is either a unit, an integer with a multiplicative inverse minus plus one. So this is like the understanding of like if you have a complex plane, you have I plus one and minus one, right? That's the units. That's the product of that's the unit. And we also have for like a what's called Eisenstein plane these units. Okay. So it's either a unit, either a prime, or either a product of primes. And we also, like we were discussing about Einstein integer, and if you wanna discuss Einstein primes, here's the description for it. It tells you what exactly the Einstein prime is. It's either a product of a unit and an integer prime p such that p mod is equals 2, or the normalization of the integer is an integer prime. Okay, so we're going to try to write a script for it in Julia. So everything we need is here. So we can come to here. And so first, there's a ways to do this. We can I'm going to just write the exact same original code that's given here. And I'm going to explain the original code. That's what I'm going to do. I'm going to choose that method of doing it. There's a lot of ways to do it, I believe. But in original code, it's, it takes this description of we're dealing with Eisenstein integers and Eisenstein primes. So this is not something defined in Julia. So we're going to define Julia about this type and its features. Okay, so in order to do that in Julia, we use this struct method or feature. I don't know exactly what to call it. It's not a function, but it's like a class in Python. So it's struct. So let's call it Eisenstein. So it basically defines a new type for Julia that you can work with, that you can create objects. And there's going to be two features of it. Like it's going to have a type for inputs that it's taken. It's going to have a generalized of the cage type, okay, which is going to be a number. So since Einstein integers are numbers, we're going to confine it with numbers, okay, number type. And the input, or let's say fields, in Julia will call it fields, it's going to take an integer, okay. Right. It's going to be an integer, like this is since in our description is given briefly, okay. Okay, so as we continue inside the struct, we can call exact A and B right here. for better um, understanding. And we're gonna just assign these two inputs or fields to the same type. Okay, but this is going to be our struct. Like we just created a struct that tells Julia that we are going to working with a new type. Okay, and it's two types of Einstein, and it takes integer, it takes subtypes of integer type, and it is a subtype of number type. Okay. And further in this structure, there's a few things we need to do, and these things are called constructors. And these constructors are basically gonna, what they're basically gonna do is gonna define the way you are gonna describe objects, okay, from this structure. So our first constructor is going to be in this form. So this is a bit of a low-level code, but structures, not all structures, I believe, need constructors, but here we may need it since we, like, in the following code, we may need to, create objects with different forms, and we need to define these different forms to our structure, okay? So the first structure is going to take inputs of A and B, and we're going to just tell Julia that this T is going to be a new type for A and B. Okay. So this code is telling you what format of object can you define. Okay. So furtherly, we're gonna we can have single inputs type of objects where T is going to be subtype of integer this time. We're going to say new T, and we're going to say we only have the A input, so we're going to keep that, but the other is going to be code 0. And here we need to indicate this subtype because otherwise we're not going to be able to apply the 0 function to it, right? So we needed to do that. Okay. And the final constructor is going to be about that you taking two integers and you want to work with same subtype of integer type, okay? So we need to do that. So it's going to be new. It's not going to be new. It's going to be it's going to be equal to T I have to check. Okay, right here. So we're just gonna say new, and this L type is basically gonna take the type of the okay, so let me explain it like this. So like I said, this constructor is gonna like equalize the subtypes of the two given integers. Okay, so these two integers can be int 32 and it can be int 64. And we need to make these same subtype, okay? I'm not sure which one would it promote to. If these are the two given subtypes, not sure. But we want to use a function that's gonna equalize, like set these two subtypes same to each other. So this function is called promote integer, okay? And we're gonna check this. This is gonna return, it's not gonna return a type, it's gonna return a type, and we're just gonna determine a type, and we're gonna use it for our low-level code. like this. Okay, so we have the t here, but which was the type function. We also have a type here, just in a different format, just to return. We just needed to determine the type of this, and we're just gonna have promote A and B, and we just have this three dots here, which you can check here. It is a actually the keyword. It's an operator for splat. So it basically does some low level things that I don't have much of a clue, so I'm just gonna skip what it is. I probably, if I'm ever need to use it, if it's ever a error like an error clause, I just need to get back and check documentations. Okay, so this is our structure. What we basically did here is we determined the types of inputs we're gonna be dealing with, and the type of or new type that we determined here. What subtype it is, number type subtype, okay? And then we have these constructors, which is telling us how we're gonna define an object, okay? What other formats we can define an object. So this is enough for talking about an Eisenstein integer. But there's going to be other features that we're going to need to determine here. For example, so we're going to work with Eisenstein prime, so we're going to need to have some operations on the integers. So in these operations, going to include real, imaginary parts. And we're also going to dealing with the complex formats of these Eisenstein primes that we need the complex numbers. So we're going to try to define these for later use. Let's start with like determining a real function for Eisenstein type. So firstly, this real function is already determined in Julia. It's under library of base. We have real function in the library of base, okay? And this real function, what it does is it takes a complex number, like z, and it returns the real part of it, okay? But here, as we discussed, the Eisenstein primes or Eisenstein integers is not exactly in the complex type. Okay, it has a component, it has a coefficient here, which includes both real and imaginary parts. So this needs to go over an operation to exactly determine restrict the real and imaginary parts. So the way we're going to do that is we're still going to call it real function. We still want to call it the real function. So Julia has a really great feature enabling us to do that by the method called overactive. Okay, so if you already have a function that does a similar, or you just want to implement a new feature to it, or you want to work with a new type, so that new type is gonna need that real function, but it's gonna have it in a different format, and Julia allows you to do that. Okay, the way you allows is that you need to indicate the type that you're going to work with, which is not going to be complex in our task. Okay, so this is the way of overwriting. So I'm just gonna now define what real function is going to do if a type of Eisenstein is given. Okay, so this is an object that real function is going to take, and this is this 4 points right here just indicate that this is the type of Eisenstein. Okay, and this function, the way this function is going to work is that, let's check here. So we got this a integer, which is real, obviously, but here we have this coefficient, the b integer. Okay, so this part, as you can see, has no imaginary unit. So this is real. and this is going to be multiplied with b, and this is going to get sum with a. Okay, so it's going to be a minus b over 2, as you can see. So let's write that down. We need the a feature of this, we determine here the field. So this n object has this feature of a integer. So we're just calling that, okay? And we say minus p n of b over 2. Right? This is the real part of an Eisenstein type of integer, right? No. So let's do the same thing for imaginary. Let's go here and call imaginary. In order to override, we also need to call actual function. And we're going to do the same thing for Eisenstein for imaginary function. And let's now determine the imaginary function here. So this is the real part. So we're not going to include a. In this part, we're going to have the coefficient b in this part. Okay, so it's square root of 3 over 2 times b. This is the order code. So n of b times square root of 3 over 2, right? So in the original code, you can see that there's this function big, which basically works for the digits after the comma. If you're dealing with really big numbers, then the big function is gonna just, what it's gonna do is just allows you to work with a lot of digits after the comma in your number. So that's basically just creates more memory thing. And you can just add it, you may not add it, doesn't matter. But in the original code, it's included, so I just wanted to also mention it. So the next thing we can do, we're also going to work with this in order to define, determine if our Eisenstein integer is prime or not, right here, as you can see. So we need to define the norm of an Eisenstein integer. So this norm function is also a function that we might into Julia, like this. We're going to call it right after we run the cell. So this norm, let's override it right here. So it's going to also take Eisenstein type. And it's basically the square of a, square of b, and minus a times b. Let's write that down. Let a times b. Let me make it more readable. Plus not a minus not a minus b plus not a. Right? This is the norm. And finally, the last thing we're going to need to do, we're going to work with the complex format of Eisenstein integers and Eisenstein primes. Okay, the complex format, I basically mean the number type, like the number, like the form of real part and imaginary part separated, and we have this, imaginary, just have real and imaginary part separated. So this is also a function that's included in complex in base library as complex. So we're going to override that function also. Okay. Eisenstein, and this is going to be we need to indicate this type right here because we're going to just determine this type as type of so this function type of is just gonna tell us the type of one of like the reason that we're doing these format is we need the type of one of these real and imaginary parts, and we want to set them equal to each other. Want to deal with different types of real and imaginary parts. We want them to same. Okay, so we're just gonna take either one of them. Like you can take imaginary, you can take real, doesn't really matter, and then you just gonna set them equal to each other. Okay, so it's going to be real and imaginary. Okay, I don't think nothing's wrong with this function, but if it does, we'll just go back to the original one and check if it's correct or not. But yeah, the aim is just to set the real and imaginary types like same to each other. Okay, not to say, not to make them equal. Okay, so this is what we did so far. We just find the structs for Eisenstein, which is gonna take integer inputs. I'm gonna talk with the syntax of Python. I don't. It's called fields here, but I don't think it makes any sense. Same inputs, and it just takes, and it's just a subtype of a number because Einstein integers are also numbers. Okay, and we just set the types for inputs, and we just define some objects, defining ways, methods. We call them constructors. Function inside structures are like method is called constructors. And then we just override some functions for Eisenstein type again, which are going to be useful for our tasks. Okay, this is basically all about like just the understanding of classes and Python. Okay, so there's just one more thing. Like there's omega, right? We also need to define that. And in the original code, they defined it in a way that was very confusing to me, but it's actually a really smart way to do it. So you have your constant v, and you define these functions. And the first thing you need to acknowledge is if you don't know, you may know it, but the Boolean is also a subtype of integer. Okay, so you can work with integers, Booleans here. So you define your constant v. Let me just write it first and then explain in this format. So it's basically, for this expression, basically is omega equals omega, okay? Just as that we just like find these functions right here. Because this object is like defined here as a way of describing. And in Julia, I'm not sure any other languages also have this, but in Julia, false equals to 0 and true equals to 1, which gives, indicate like this, which gives an Einstein integer of 0 plus, since this is A, corresponds to A and this is B, 1 time omega. Okay? Since this is 1. So this expression is directly equal to omega. Okay? This is a good way to, you know, describing it. It is very smart. So anytime that you're going to work with this object, the way you define your A and B, your function is going to give you this. So you're going to be able to like take your omega out of the equation, just like that. Okay. So this is okay. So this is basically it. We called more. So in order to override your functions, you also need to call them, and we did that. So the next thing we can do is we also need to add these begin and ends keywords in order to not get the so it runs it. I didn't want it to run it, to be honest, because I'm gonna import other things in the future. But let's see if it got any errors. It did. Something like that. Okay. It's not even an actual error. Okay. So next thing we want to do is to check. So here we can create an object in Eisenstein struct, which basically corresponds to Eisenstein integers, right? So the next thing we need to do, if we are now able to generate Eisenstein integers, is to check if they're primes or not. Okay, and then we're going to work on these primes, and we're going to need to generate primes also. But at this point, all we need to do in this next cell is to check if an Eisenstein integer is prime or not. Okay, so I'm going to define a function which is going to call is Eisenstein prime, and it's going to take an argument of an Eisenstein object, of course, right? So inside this function, what we need to do is we need to check the description first. So we need to understand what's an Eisenstein prime. We can just go over it again, and we're going to be able to indicate it. Okay. So an Einstein integer a plus b omega is a prime if either it is a product of a unit and integer prime p such that p mod 3 equals to 2, or so we get this or, and here is going to be very useful in our code, or normalization of a plus Einstein integer is an Einstein integer prime. Okay, so let's do it. So product of a unit, I already described what it is. There's a method to do it. I'm just gonna write down the method, which you check if your a integer is a 0. So consider the case your a integer is a 0, then you're gonna be left with b omega, right? So b omega is a product of a unit, because if you recall the product is a so it's becoming a product of a unit since you know the units. Okay. And the second thing we check if for phi is a 0. Okay, if phi is a 0, you're left with a, which is product of units. Okay. And the last thing we check is if, sorry, by the way, the a and b needs to be called by an object. Okay, so the last thing we check, and b equals an a. This also enables that you have, so if these are equal, then you have a equals to b, then you have, you can just have it in a parentheses like this, right? And as you recall, one would be good. Let's one. Sorry, omega plus 1 is equals to 0 minus 1, right? So if you just open this expression, you're left with 2 plus omega plus 1 equals to 0, right? If you, with, with this quality, you have this, which is here, as you can see. If you just have it on the other side, then you're just left with this minus v squared, and v squared is a unit, then you just have a product of unit. I'm not sure why I struggle too much to explain this, but that's the case. I just do it. And then this if we're just going to check these conditions, and if they're matched, then what we're going to do is we need to you need to define a new C number, which is going to be max of absolute value of n with a or n with b, right? This is basically a good way of description. Like you have the maximum amount for C. We're just looking for this which is prime. So this maximum value, if a is 0, it gives you b, if which is the only thing you have. If your b is 0, you take a, which is the only thing you have, and if they're equal, it just returns also whatever you have, right? So we just set that to c, and we need to check. Okay, so we need to check if this is a prime. And in Julia, we have a function for it, which is called is prime, and we just need to call it, okay, from primes. And it's called is prime. Oh, sorry, so this is all about that. Surely, what would the so we're gonna be calling is prime here. For now, I'm just gonna write it down. Is prime, we're gonna check if C is prime. And we also can check this condition right here given the mode tree. The C mode tree equals 2. This is gonna return true or false, right? We're gonna have a true or false value. So the next thing we're gonna do is gonna end this. No, we're not going to end it. We're going to have an else structure, and then we're going to check if these are not the cases, then all we need to do is this, check the normalization, right? So it's going to say it's prime again, since it's just a number, norm n, right? And we're just going to end it. So this is our function to check if the given Eisenstein integer is a prime or not. This is basically very smooth code. Just checks. It just returns whatever you need. So let me just run this line first. And then I'm gonna do the other one because we call it is prime, but we need to call it here. I'm doing the importations later because I wanted to show where I call it. I didn't want to do it in the beginning. Base is basically just like this, huh? Okay. But the others have this is also a work. So we find our function. Okay, so now we are able to generate an Eisenstein integer, and we're also able to check if it's a prime or not. Okay, the next thing we're going to do is just going to now skip to our task. Our task wants us to print out the first 100 Eisenstein primes near 0 by norm order. So this it's going to be a function. It's going to be in function form. So let's define this function. Now let's call it, for instance, b primes, let's say. And it's going to take, it's going to take a few values, few inputs are going to be here. So the first, there's things that we need to check. The first thing is that it's want us to print out the first 100 primes. Okay. So there's a limit. So let's first describe that limit. Okay. Call it print limits, which will be same in the original code. And the second thing that we need to check is we're gonna need an area to find that 100 Eisenstein primes. Okay, so this is something that like confused me, and I asked it here. So my question is that with the loop that we're gonna just write here, it's gonna generate like around like 40,000 Eisenstein integers. But my question was like is it ensures that it's gonna include at least 100 Eisenstein primes? So it's the person said, um, so I didn't know this because I'm not an mathematician. I didn't know that we expect there to be lots of Einstein primes near zero. I didn't know that. And it's like you're just gonna check if you do have 100 e primes, and if not, you're just an increased area. That's the. But there's also further math in the following, but I just have no idea how to read this and understand. So I'm just gonna stick with this idea. So I think since they expect to have a lot of e primes near zero, then I think this 40,000 minus 9 should be sort of like pretty enough to do it. And in the original code, I think like there's no math like this. It's more like it's gonna be more the way we're gonna do it right here. So it's gonna grab the square, set it to 1,000, and I'm just gonna have this limit to generate Einstein. So let me explain what this function is going to do right here. There's a few things that it needs to do. So we need to, so we want to work with Einstein primes. And what we have is an Einstein integer structure that we can like define objects that corresponds to Einstein integers. And we have a function that can check if that object, or let's say the Einstein integer, is prime or not. Okay, but in order to do our tasks, we need to work with so this function is going to work on generating an array of Einstein integers and then checking that if that array's elements are primes or not by applying this function that we just defined here. And instead, we need to also sort them by the norm order. Okay, so we're gonna do this in this function. So let's focus on generating Einstein integer array. Okay, so we're gonna describe a limit for this like array length, which is gonna be it's basically focused on creating an area near zero, like from zero, and it's gonna check if Einstein primes are there or not. And if that area is big enough, then we have that we're gonna have like enough Eisenstein primes, and then we're gonna be able to print them by limiting by this print loop. Okay, so let's just take this, copy, paste. So this function also right here is integer square root. So it takes the square root and it rounds it to the nearest integer. Okay. So let's create an array. I'm gonna call this array, and array is gonna be made up of Einstein integers, and the way we're gonna do it is creating like an object, the Einstein struct, and this Einstein structs, the objects we'll be generating here can be in a loop for A and B. In the formats, since we want it to be around like nearest zero, we'll like consider like an axis nearest zero, then you're gonna have like a symmetry around that axis. Okay, so it's gonna be from -2 plus -2, yeah. Okay. So and that's axis is gonna be from limits to plus limit, minus limit to plus limit, and the limit is just described here. Okay. And we're gonna do the same thing for B. And this loop is gonna combine a lot of A and B pairs, and it's gonna create objects in a loop, and it's gonna just assign it to the array. Okay. So we're just gonna be generated an array of integers, Eisenstein integers. So this is what it does. So now this line, this piece of code, we have an array of Einstein integers. And the next thing we wanted to do in this function, we want to create an array of Einstein primes. And in order to do that, we need to work with this array of Einstein integers. And the elements are needed to be like this function is needed to be applied to elements of this array. So there's a function for that. Let's firstly name our array of Eisenstein primes, which I'm going to call E primes, and the original code is also called E primes. And so this array, firstly, like I said, we need to apply this function that checks if an Eisenstein integer is an integer or prime or not, and then keep that information, right? So in Julia, we have a function for that, which is called a filter, which takes an array, which takes the function first, sorry, which takes a function and applies that function to the array that is given. And this needs to be a Boolean function, I believe, for filter. Function that's given here should be a Boolean function because it's going to return an array which is going to return an array of elements that returned true Boolean. And it's going to just keep those like true returned elements, okay? So this is going to be an array of Eisenstein primes, actually. This is enough code for us to generate an E primes, like Einstein primes, using our array of Einstein integers and our function of is Eisenstein prime. But the last thing we need to do with this, array primes is we need to sort them. And we can do this just in a single line. I'm just trying to implement the original code here. So I'm like trying to do it step by step, but I'm also trying to do the same thing. So it can kind of be a bit complicated. But in original code, E primes is generated and also sorted by the function of nor, just in a single code. That's what I'm trying to do. So we firstly filtered this array of integers as checking if it's prime or not, and we're just left with E primes. And now we're going to sort this array. We're going to sort E primes. We need this also by a function of norm. Okay, so the way we're going to indicate that is sort function first takes this array, and then it takes this function, which is if you can just leave it as LT, which like corresponds to less than, but we're gonna override this function again. It's gonna take x and y, and it's gonna check the norms. So this function right here just indicates that you check less than by in terms of norm, okay? By in terms of norm function. And this sort function right here takes this function and sorts this array in terms of that function, which is a great function, which makes this a lot easier for it to do. Okay, so we just have this sorted E primes. So we're going to use that. So we're going to display a function. So what we need to do right now, we need to go through the print limit. We need to go from 1 to 100, and we also need to go through the elements. So also there's a function for that in Julia that takes two iteration elements, let's say, uh, in numerate digits. Right? So this enumerate is the function that's the original function and enables you to use this format of two iterations. Okay, so it's going to take two iterations, and as long as e primes is smaller or equal to print limit, print limits. So in case we're gonna print what it wants to print complex number values. I'm gonna complex the complex C. C comes from this. It takes the elements, okay? It takes the E primes I corresponds to that. In Python, you need to indicate that, but here you don't. So this basically works. Let's say those end the for loop. Is there anything we need to add? Don't think so. Let me check. We'll later on plot it, but here right now we don't have any that. So let's only get 20 primes like this, right? Okay, so here we have it. We can make this better. We can make this better looking by lowering the number of digits, right? So it's going to be around 4. It's going to be just 4 digits 4. We can apply a lead path, which kind of, make it look better. Lead path, so to make the integer value. And thirdly, we can do something like this. So gonna like give a line as we reach 4 amount of elements, right? I hope I wrote it correctly. So let's take the parentheses. This is leaf pad. This is round. This is complex. Okay. So, see, it's better. You can read it better. So the first task is complete. What we did again, we created a struct called Eisenstein, which takes integer values as some type of a number, and it has a ways of finding an object, and it has this overwritten functions that were useful, as you can see here. Complex, for example, it just gives us the complex format of the Einstein struct. So this is not an Einstein integer. This is an Einstein complex. So Einstein, it's a complex number. But here, your actual objects you can create the struct gives you an Einstein integer, which is not a complex number. Okay, so this functions that's helps you do that basically. I don't think it requires more further explanations anyway, but I just also need to mention it. Okay, so the next tasks. Oh, we only have one. So we need scratch. Scratch, sorry. We need to plot. So the way we're gonna plot. Sorry, what I did is I used Python shortcuts. Here, the way you create a new cell is just CTRL enter. Okay, so we need a new function that's gonna plot the first 2000 such numbers. So we're going to need the real and imaginary parts of this complex number to plot, right? In the complex plane. So let's create a function. Let's call it plot e primes, which is going to take e primes, right? And we can just set this, since this is just prints out e primes. So we can just set it here, and we can also return e primes here. This is just the same and title. Okay, so furtherly, we're gonna create this function that's gonna plot. So you need to get back here, and we need to port plots under. We need to call scatter, and we're just gonna say using plots. And one of the things that we also need to do is we need to call a backend, which is called gr backend. So we are not defined because we need to run this again, because it's going to call plots. Then this is going to be realizable. Let's write our function for plotting the prime. We're going to need, like I said, real and imaginary parts. So let's first define the real parts. How are we going to able to generate? How are we going to be able to detect the real parts? So verbally, we need a function that's gonna apply this overwritten function right here to elements of an Eisenstein integer or prime. Sorry, we're working with primes. We also have a prime, e primes array. So we have four elements, and so we're just gonna need to take that e primes array, and we need to apply the real overwritten function to it, right? So I hope this is okay. Until for a second we were streaming. Okay. The real parts are gonna be, so there's a function in Julia does that called map. So it takes the function and applies to the array you give. So and returns every element, okay, for a function that you give here. So it applies to each element and it returns each element with the operated form. Let's do it for imaginary parts too. Image e primes. And then we're just going to plot this. Okay, we call it scatter as you recall. And we're going to take real parts. One of the worst things in Pluto, there's no like auto suggester. You know, I'm just when I type RE, it could have just suggested me real parts, right? Then I can just tab and continue, but it doesn't have it unfortunately, maybe in the future. And there's other features for the scatter function. So you can just label it. Let's label it E primes. You can give a marker size. Let's give it 2 and then give it 1. Okay. I think this is gonna work. I think this is enough. Let's call the function. We also need to call this. I called it with it. Well, gr backends here, and we're just gonna give e primes that we. Oh, I'm sure that this is. I feel like I'm forgetting something. It should have been given here the things that I needed. Maybe I should call it from the beginning. Okay, right here. So we didn't like run this cell. It includes return. We just added return. It needs to return eprimes, and it's gonna just show us here. Okay. Okay, let's run this. When we need to see something like this. We can change the marker size later. Ooh, this is not. I think it one. This is not correct. What are we missing? Uh, this is not correct. Is there something wrong here? That was 200. We probably done something wrong, but I'm not sure what. We need to debug it. Um, must be here, right? So this is the real part. Oh. Okay. It's gonna run everything again. Okay. I just wrote also A here. Okay. So this is exactly what it is. Let's do it with marker two. 'Cause I really like these markers. Let's see all of it. Like also three. Gonna give it bigger. Yeah. I wonder what would it happen if you do 10. Okay. So we're gonna put. Okay, so that's what it is. Um, let's go. Yeah, that's prime near zero. So yeah, like the guy on the sport mentioned, it apparently does uh, lots of files and of zero. Yeah, exactly. It's more that's right here, right? And there's less density. Beautiful. Okay, let's go. We can start.